Very good morning to all of you. So last time we have studied four iterative schemes for solving the system Ax equals to B numerically. If we wish to write the general iterative scheme was Qxk is equals to Q minus A x of k minus 1 plus B, where Q is called splitting matrix. Okay, and for Jacobi method, if you recall, is given by, if you take Q is equals to D, so where D is the diagonal matrix whose diagonal elements are the diagonal elements of A. So D is a diagonal matrix where you can say D of I comma I is equals to A of I comma I. Okay, for Richardson method, the splitting matrix was identity matrix. For Gauss-Siedel method, the splitting matrix was Q is equals to L plus T. So L is the strictly lower triangular part of the matrix A, which has been explained in the last lecture, and D is the diagonal part of the matrix. Okay, right. So for successive over relaxation method, if you recall, Q is equals to W inverse time D plus WL. So where D is the diagonal part of the matrix A and L is the strictly lower triangular part of the matrix A. Okay, so these are the four methods we have learned, and these all methods will converge for sufficient condition. Okay, so if I wish to write, the convergence is guaranteed, converges if log of I minus Q inverse of A is less than 1 for some subordinate matrix norm. Okay, so not that this is a sufficient condition, not necessary. Okay, means if this condition fails, means you are not able to recognize with respect to what type of subordinate matrix now this condition is satisfied, then the method may or may not converge. Okay, so for an example, let's consider the following system. So if you look at the coefficient matrix, and if you carefully extract the coefficient matrix A into three parts, L plus D plus U, where if you recall, L is the strictly lower triangular part, D is the diagonal part, and U is the strictly upper triangular part of the matrix A. Okay, and now if you test the sufficient condition for Jacobi method, okay, then what you will get is the following. That so for Jacobi method, if you try to get I minus Q inverse of A, or this is equals to Q inverse of Q minus A. So for Jacobi method, that is equals to D inverse of L plus u. So for Jacobi method, you need to satisfy the sufficient condition for the convergence of the scheme. Okay. Now note that if you try to calculate the infinity matrix norm, that is come out as 1.5. That you can check with the help of Matlab code. So norm, infinity norm is already exist. Okay. There is a function. Okay. So you can just take the function norm. Okay. And the matrix, and you have the infinity matrix now, comma inf. So that will, so D inverse of L plus U. So that will calculate the infinity matrix norm for the matrix. Okay, right. So that you can also straightforward use. Okay. So this condition is not satisfied. Okay. So what you can do? So this so you require necessary and sufficient condition. Okay, so that you can guarantee that whether the method converges or does not converge. Okay, so we are going to derive now the sufficient necessary and sufficient condition for the convergence of general iterative scheme. Okay, right. So the Neumann series already being covered. Okay, which essentially approximate inverse of the matrix A. Okay, so if you if I recall that A is a n cross n matrix whose norm is less than 1, so some subordinate matrix norm. So unless it is mentioned, we are talking about subordinate matrix norm. Then I minus A is invertible, and its inverse can be approximated by the sum of the powers of A's, and whose bound is also can be calculated. Okay, so this has already been seen, so this thing you need to calculate. Okay, right, since norm of A is less than 1, so this series, the right side series, will converge to 1 minus norm A to the power. Okay, this series will converges, and you have, if you look at this norm, this converges, right? So this is less than equals to summation k equals to 1 to infinity norm of A to the power k, and which is equals to 1 minus norm A inverse. Right? Okay. Since norm is a continuous function, if you recall. Okay. Right. The next is a very important result, which will be help us to decide the necessary and sufficient condition for the convergence of general iterative method. Okay, so this result tells you that the spectral radius function satisfies the following equation. So if you recall the meaning of infimum, so what is the meaning of infimum? Infimum is means greatest lower bound. Greatest lower bound. Okay, and then take the infimum over it. That is actually equals to spectral radius of A. So one way is very much clear. Okay, so if you try to look at the proof, so one way can be given easily. Okay, for the other way you have to look at the reference book by Kincaid and Cheney based. Okay, so we have already seen that for any subordinate matrix now, spectral radius of A is less than equals to norm A. For all subordinate matrix now, that we have shown in the very first lecture of norms on matrices. So therefore this implies spectral radius of A is certainly less than equals to infimum over all subordinate matrix norm of norm A. So this way is very much true, okay, and this is obtained easily. For the other way, you require the concept of similar matrices and other things. Okay, so which is not in our scope. So that's why we are skipping. So but however, if you are interested in the proof, you can refer the page number this, or you can also contact me. Right. So now we have, okay, so in order that iteration formula xk equals to g of xk minus 1 plus c. So if you recall, what is the general iterative scheme? Theoretically, if we rewrite xk is equals to I minus q inverse of A x of k minus 1 plus q inverse of B. So if you, so this is general iterative scheme for general splitting matrix. If you wish to write in the following form, then G is equals to I minus q inverse of A and C is equals to q inverse of B. So you can adjust the things, okay, right. So in order that the iteration formula produce a sequence converging to the following, that we are going to show that the sequence converges to the following for any starting vector. So this is very much important. So for any starting vector, so you can take any initial starting vector x0. So you can initiate 0 0 0 0 vector, or you can initiate all elements equals to 1. Okay, so this is very much important statement. Then it is necessary and sufficient that the spectral radius of G be less than 1. Means this necessary and sufficient condition is spectral radius of G is less than 1. If and only if. Okay, so we wish to prove this. Okay, right. Right. So we wish to prove the following. So let's prove this. Okay, so let spectral radius of G is less than 1. So this implies, so you know spectral radius of G, okay, this implies norm of G is less than 1 for some subordinate matrix norm. So we are choosing that same norm. Okay, so norm of G is less than 1 for some subordinate matrix norm. Right? Okay. Now x k plus 1 is equals to G of x of k plus c, which is equals to G of xk minus 1 plus G square xk minus 1 plus G c plus c Now we are using here, not that, we are using this recurrence relation repeatedly. So what we are going to observe? So xk is replaced by g of xk minus 1 plus c. Okay, so this is further, this is equals to g cube xk minus 2 plus g square c plus gc plus c. Right? Now if you go one more step further, this implies x of k plus 1 is equals to g to the power 4 xk minus 4 k minus 3 plus summation j is equals to 0 to 3 g to the power j c. Right? Okay, and so on. So this is equals to g to the power k plus 1 x0 plus summation j equals to 0 to k g to the power j c. Right. So now norm of g of k plus 1 x0, if we wish to calculate this as k goes to infinity. So this is, so since this is subordinate matrix norm, so this is less than equals to norm of g to the power k plus 1 time norm of x0. So norm of x0 is fixed, and since subordinate matrix norm is submultiplicative, so if you use the property, this is less than equals to norm of g to the power k plus 1 time norm x0. Now since norm of g is less than 1, so norm of g to the power k plus 1 tends to 0 as k tends to infinity. So this implies in the limiting case, limit k xk plus 1 is equals to summation j equals to 0 to infinity z to the power jc. The first term tends to 0, and if you recall, this is nothing but summation j equals to 0 to infinity z to the power j. We can also write this as c, and this is equals to, if you recall this Neumann series, this is equals to I minus g inverse c. So if the spectral radius of g is strictly less than 1, then the sequence produced by the general iterative scheme converges, and it does converge to the following quantity, following vector. Okay, right. Now what about the converse? So conversely, let limit k x of k is equals to I minus g inverse c, converges. Okay, what we wish to claim? So our claim is, okay, our claim is spectral radius of g is less than 1. So let, not true, okay, spectral radius of g is greater than equals to 1. Okay, this implies there exists a lambda, okay, such that mod lambda is greater than equals to 1. Let u belongs to Rn norm of U, the subordinate matrix, subordinate norm, one of the norm on Rn is 1. Okay, is such that G of U is equals to lambda U. So that is possible. Let x0 is a 0 vector. Okay, now for lambda equals to 1 and C equals to U, we have xk plus 1. If you recall from the previous recurrence relation, that is equals to summation z equals to 0 to k z to the power j u, and first term is 0 because x0 is a 0 vector, and this is equals to, if you apply that g of u, gu is equals to lambda u. Okay, so this implies this is equals to k time u, k plus 1 time u. This is equals to k plus 1 time u, which tends to infinity as k tends to infinity. Okay, right. Now for lambda not equals to 1, c equals to u, what we have is we have x of k plus 1 is equals to summation z equals to 0 to k gju is equals to summation z equals to 0 to k lambda j u is equals to lambda to the power k plus 1 minus 1 divided by lambda minus 1 time u. Since mod lambda is greater than 1, therefore limit lambda to the power k plus 1 does not exist, and this implies limit k xk does not exist. Right? But this is the contradiction to the fact that iterative scheme produces a sequence which converges to certain vector. Hence our assumption is wrong. Therefore spectral radius of J must be strictly less than 1. Okay, so this gives us the necessary and sufficient condition for the convergence of general iterative scheme. Right. So now let's go back and check the previous system itself. Okay, where we have seen the following, that if you take the infinity matrix norm for the general iterative scheme, okay, for the general iterative scheme for G is equals to I minus Q inverse of A for the Jacobi method, that is 1.5 and that is greater than 1. So that gives you Jacobi method need not converge. However, if you try to evaluate the spectral radius of the same matrix, then it is going to be strictly less than 1. So this guarantees that Jacobi method would converge for any x0. So we can work with any x0 and we can apply Jacobi method for this system. Okay, right. Now some of the convergence criteria, sufficient conditions. So for the Richardson method, so the Richardson method converges if either of the following is true. The first condition is the matrix A has the property. So if a matrix A has the following property, means the diagonal elements are equals to 1, and the sum of the other element in the same row in magnitude sense is strictly less than 1, then you will call that unit row diagonally dominant. Okay, so for example, if I have this, so 1, let's say 1 by 2, 1 by 3, 1 by 2, 1 by 3, 1, 1 by 3, 1 by 2, and 1. So if you look at A11, A22, A33, so they are equals to 1. Right, that's the first thing. The second thing is the sum of other elements, so 1 by 2 plus 1 by 3 should be strictly less than the, so here you are talking about first row, so A11. For the second row, if you are looking A21 magnitude plus A23 magnitude is strictly less than A22. Similarly for the last row. And if the matrix A has the property unit column diagonally dominant. So if you are looking in this way, then also it is unit column diagonally dominant matrix. So either of the condition is true. Okay, then the Richardson method will always converge. Okay, right. The next here is the very important result. So this result give you the sufficient condition for the convergence of Jacobi method. So which says that if A is diagonally dominant. Okay, so let me define when you will say a matrix A is diagonally dominant. So we say that a matrix A is diagonally dominant if summation j is equals to 1 to n, j not equals to I, mod of aij is strictly less than mod of aii. For every 1 less than equals to I, less than equals to. So we say that a matrix A is diagonally dominant if the following condition is true. Okay, so you are going to look at in the particular row accept the diagonal entry. So you are going to sum up the, so if I wish to give an example, the same example 1 by 2, 1 by 3, 1 by 2, 1 by 3, 1 by 3, 1 by 2, 1. So if you look at, so here, so A12 plus A13 magnitude is strictly less than mod A11 with respect to the first row. For the second row, you have to look at mod of A21 plus mod of A23 is strictly less than mod of A22. Similarly for the third row, so mod of A31 plus mod of A32 is strictly less than mod of A33. So this is an example of a diagonally dominant matrix. So if a matrix is diagonally dominant, then the sequence produced by the Jacobi iteration converges to the solution for any starting vector. So again you can choose here any arbitrary initial vector. Okay, right. The next result is for the Gauss Siedel method. So which states that if A is diagonally dominant, then the sequence produced by the Gauss-Siedel iteration converges to the solution of Ax equals to B for any starting x. So again, so this both results tell you that if A is diagonally dominant, then whether you use Jacobi method or Gauss-Siedel, both converges to the solution of the system for any starting vector. Okay, right. So proof of Jacobi method is already done, and for Gauss-Siedel method now it is easy to prove by using the sufficient condition. Okay, so that you can look at. If you are not able to get, you can ask me. Okay, right. So the next result is for the convergence of the SOR method. So what it is saying is, if in the SOR method, suppose that the splitting matrix Q is chosen to be the following: alpha D minus C. So here in the SOR method, you are allowed to choose a matrix with complex entries. Okay. Now suppose that the splitting matrix Q is chosen to be, so Q is equals to alpha times D minus C. So if you recall the general method, if what SOR method we have learned is Q is equals to W inverse times D plus WL. Okay, so here alpha is W inverse and C is minus L. Okay, you can compare for the previous method, previously stated SOR method. So here alpha is a real parameter. Now D is any positive definite Hermitian matrix. So if we recall, a matrix is positive definite if X transpose of AX. So we can say that a matrix A is positive definite if X transpose AX is greater than 0 for every X non-zero. Okay, right. So there are other criteria as well for positive definite. If all the eigenvalues are strictly greater than 0. Okay, right. That's also one of the criteria. Now note that we are talking about is any positive definite Hermitian matrix. So we are talking about symmetric. Okay, so we are only case when our entries are real. So here D is any positive definite symmetric matrix and C is any matrix satisfying the following: C plus C star equals to D minus A. If you recall, what is C star is complex conjugate transpose. Okay, so here we have assumed that for the SOR method, the matrix A is symmetric. So we have recall, if you recall from the session what we have told during Cholesky decomposition, that a symmetric matrix is positive definite if and only if all leading principal minor are strictly greater than 0. Okay, so here what is required now is, so here L, what is C is here is minus L minus U. Okay, C is equals to minus L. Okay, since A is symmetric, U is nothing but L transpose. So okay, so C is equals to minus L, if you recall from the previous lecture. Okay, right. So if A is positive definite Hermitian, means if A has real entry, is a positive definite symmetric matrix. If Q is non-singular and if alpha is greater than half. then these three criteria will give you the convergence of SOR method. Okay, right. So we are going to work for the SOR method. We are going to make sure that matrix is symmetric. Okay, and then we can extract C from there. We can choose W as, so 1 by W is equals to alpha. Okay, 1 by W is equals to alpha. So alpha is greater than 1 by 2 means W must be less than 2. Okay, so if you want to relate from the previous lecture, okay, so here you can choose any value of W between 0 to 2. Right. Now we are going to define the rate of convergence for iterative method, general iterative method, which is given by the following term: T equals to minus log with base 10 spectral radius of G, or with the natural log. It depends with which log you wish to work. Okay, so where rho of G is the spectral radius of G, and then quantity minus 1 by this one represents the minimum number of iterations required. So if you recall that, if you note that here iterations, number of iteration is an integer number. Okay, so you have to make sure that you are taking the nearest integer next to it. Okay, right. So now whatever we have learned so far, so now we are going to see the result on Matlab. Okay, so we are going to look at the methods and we'll see how we are going to fix the sufficient conditions and how we are going to check the necessary condition for the convergence and how they will work, what will be the speed, what will be the comparison. So we are going to discuss now. So let us look at the Richardson method first, and see the first here we have applied the while loop, and so we have asked the user to input the coefficient matrix A. Okay, and the next here, if you look at here, okay, so this will decide the size of the matrix. So if matrix is a square matrix, then you will be come out from the loop. Otherwise the user will be here unless he entered the square matrix. Okay, then we have asked to enter the right hand side. Okay, now we are trying to make A as diagonally dominant here through row interchange. So we are only allowing row interchanging so that the matrix becomes diagonally dominant. Okay, right. The next loop is, so here we wish to make the singularity test. We have to make sure that the matrix is not nearly singular, so that the system has unique non-trivial solution. Okay, right. So this is where we are having, so we have made the here tolerance of singularity test, that is 10 to the power minus 4, and we have defined, so we are going to test whether all the minors having the value greater than singular test or not. So if one of the minor is less than equal to singularity test, then the sufficient condition for are not true, and you will be represented with the following error. Okay, so if you feel this is necessary, you can also fit into it. Okay, right. Now the next we are going to check whether the entered matrix is well conditioned or ill conditioned. So we have checked by we can check with respect to infinity matrix now. Okay, so this is where we have calculated the infinity matrix norm for inverse and matrix, and then see if whether the condition number is less than equals to 200, then we will say it is well conditioned, and enter matrix. If otherwise, if k is greater than 200, we will say the matrix is ill conditioned. Okay, so this 200 number, that you can decide, you can make it 400 or 500, that's up to you. Okay, right. Now the next we are going to check that unit diagonal dominance of matrix. So we are going to check in terms of row diagonally. Okay, unit row diagonal dominant, whether the matrix is, so next we are going to check whether the matrix A is unit diagonally dominant or not. Okay, so this is the loop here. So we have make here you can say if AII is equals to 1, so we need to make sure that all the diagonal entries are 1, then only you will enter into the loop, otherwise it's break. Okay, so we have make sure that if AII is equals to 1, then you take the sum of all the values in the particular row except the diagonal entry, and see whether in absolute sense whether the sum is greater than equals, whether the sum is greater than equals to 1 or less than 1. If it is less than 1, you have the unit diagonal dominancy of the matrix. Okay, otherwise it is not. So we have called some temporary variable that is equals to temporary 0 if it is not unit diagonally dominant. Otherwise you have, if it is true for every, then it is equals to temp equals to 1. Okay, otherwise else temp equals to 0. If AII is not equals to 1, we have called temporary variables are 0. Okay, right. Okay, right. So next we have decided the error tolerance. Once we have gone through the sufficient condition, we have decided the tolerance, that is also is 10 to the power minus 5. Okay, so if temp equals to 0, if you have the value temp is 0, means it is not unit diagonally dominant, then we cannot leave the matrix as it is, so we check the necessary and sufficient condition. Okay, so for checking the necessary and sufficient condition is here, this is here, we have checked the condition. So splitting matrix for Richardson method is identity matrix, if you recall, that is of order n, and you have the initial arbitrary 0 vector. Okay, and if this condition satisfied, so spectral radius of the matrix I minus Q inverse of A, if you recall. Okay, so here QR is I, identity matrix I minus A will be there. So the Richardson method converges. And the next statement, if you recall from the last slide, that how will you find the rate of convergence for the particular method is by the following formula: minus log of spectral radius of the iteration matrix. Okay, right. So once you entered into the loop now, okay, so if temp equals to 0, this is things are going on. Now here we have already asked the B vector, right? We have already asked the input B vector. Okay, so we can here, so here is no need for this. Right? Okay. Okay, right. Now, so here is, this is, we have decided here the maximum number of iterations. So we have decided maximum number of iterations are go up to 100 number of iterations. Okay, and then we have we have carefully fixed the for loop so that we will get the updated approximation, okay, after each iteration, okay. And so we have calculated the new value x, and then we will say error value is given by absolute of x2 minus x. If error value is less than or equals to error, then it breaks, and then it display the solution set and the number of iterations. So if it is suppose at 50, now if within 50 number of iteration, if you achieve the error tolerance, then you are out of the loop and you will display the solution set. So this is what the objective for putting break here. Okay, right. Now else display the Richardson method does not converge. Means else means you thus the necessary and sufficient condition does not satisfy. Okay. Now else, so this else here is for if temp equals to 0. If you look at here, if temp equals to 0, if you look at here, this is setting for this. So if temp is not equals to 0, then it will get down here. Okay, right. So means this means temp is 1, means the coefficient matrix is unit diagonally dominant. So we no need to check the sufficient necessary and sufficient condition. So already sufficient condition true. So Richardson method does converse, and then we have applied the same thing here to get the value. Okay, so let's run this. So if we run this and let's have the following matrix, okay, and let's have the following vector. So entered matrix is well conditioned. The answer, okay, means the condition number is less than equals to 200, and the next statement is the coefficient matrix is not unit diagonally dominant. Okay, we checked necessary and sufficient condition. Still necessary and sufficient conditions are not true, so the Richardson method does not converge. So if I write the A here, so you can look at here that it is not unit diagonally dominant. So A matrix is 2. So you take C A11 is 2. Okay, and this is certainly not equals to 1. So this is not diagonally dominant matrix, unit diagonally dominant matrix. Okay, and also note that we have entered the matrix in the other form here. Okay, so we have made the row interchange possible, okay, through that loop, so that it becomes possibly diagonally dominant at least. Okay, right. Let's run again the Richardson method, and let's replace this 2 by 1. Okay, right. And now this is okay. Yeah, so entered matrix is well conditioned. Okay, the coefficient matrix is unit diagonally dominant. The Richardson method converges. The rate of convergence is 0.18232. Enter the constant vector B. So this is again, it is asking you to enter, and the solution set is 1 by 3, 1 by 3, 1 by 3. So that you can number of iterations it execute is 62, not complete 100. Okay. So here also this is not required. This is okay. Right. Okay. So if you again just run again for the same method, you have got the within 62 iteration the same. Okay. So we will run this with the Jacobi method as well and Gauss Siedel method the same thing. So let's go for Jacobi method. So for the Jacobi method, if you look here, okay, the first proof is as it is. Second proof is also to make A is diagonally dominant. That's also fine. Singularity test is also applicable there. So that is also the similar. Then checking condition number, well conditioned or ill conditioned. That's also the same. Checking diagonally dominance of the matrix A. So here we are not restricted that AIIs are 1. Okay. So here we have gone without AII is equals to 1. So we have checked carefully, put the diagonal dominant or not. Okay. Now if it return temp equals to 0 means it is not diagonally dominant, then it will go for executing the necessary and sufficient condition. Okay. So x equals to, that's initial 0 vector. So this is the initial 0 vector and this is the extracting diagonal part of the matrix A. Okay, and here it is the splitting matrix for Jacobi method. Okay, right. The next here is we have put down the loop for let's say suppose one of the diagonal entry is 0, then what will happen? Then you cannot execute because you are going to have, if you look back and see, if you go back and check that DII are going to be in the denominator. Okay, when you are going to apply the method. So we need to first check that whether all DIIs are greater than 0 or not in absolute sense. So this is why this condition is there, and else, okay, if it is not, then it is not possible. Okay, right. Then you have checked the sufficient condition and then you have determined the speed of the convergence, and this is the iteration matrix. Okay, right. And then you have carefully write the code for getting the values, updated values for given arbitrary vector. Okay, so this is the main loop here, which will give you the updated x value for any arbitrary initial vector x0 by using Jacobi method, and then you have displayed the solution of the system. Right. Otherwise, you have, if one of the diagonal entries absolute sense is equals to 0, then the splitting matrix is singular, so you cannot apply the Jacobi method. Okay, and here this is if tap equals to, so if tap equals to 1 means the coefficient matrix is diagonally dominant. There is no need to check the necessary and sufficient condition again, and you can again apply the similar manner the Jacobi method. Okay, so let's run the code for this. So let's have this same matrix. Let's have this. So it also takes 62 number of iterations. The rate of convergence for Jacobi method is 0.18232, which is the same as for Richardson method, and solution set is also same. So no change here. Okay, so let's run Jacobi method again. Now let's consider the previous matrix and previous constant vector. Yeah, so Jacobi method does converge for this. However, Richardson method does not converge for this matrix, which we have seen already. Okay, so this method is applicable to that system, okay, which is not solvable by Richardson method. Okay, right, and it takes number of iterations are 28. So if you look, the number of iterations 28, and the rate of convergence for this is 0.4268. Right? Okay. Now let's see the Siedel method. So everything is almost same, only you need to put the forward substitution, okay, in the Jacobi method carefully. Okay, right. So this is the main loop which we have used for the forward substitution method. Okay, so that you can look at carefully. Okay, so and carefully we have extracted the splitting matrix. Okay, splitting matrix, and we have also okay, so we have we have extracted the lower terminal part of the matrix A as a splitting matrix for Gauss-Siedel method. Okay, so let's run the code for Gauss-Siedel method. So let's go for the same matrix. With the same matrix. So now if you see and check, okay, so Gauss-Siedel method, the rate of convergence for Gauss-Siedel method is 1.589. However, for Jacobi method was some 0.42. Okay, and the solution set is obtained, then the number of iterations are 8, and in Jacobi method it was 20. So it is faster than the Jacobi method, that we can conclude. Okay, right. Right. Okay, so let's consider for this, which we have also checked with the Jacobi method and Richardson method. With the both it was convergence. Now see, for this number of iterations it has taken only 10, and Gauss-Siedel method is rate of convergence is 1.2425. Okay, however, in the case of Jacobi method and Richardson method, the number of iterations, if you recall, that was 62. Okay, and the rate of convergence is near about 0.18 something. Okay, right. So that you can see the difference between. Right. Okay. So if you have any doubt, you can still ask. Okay, through email. Okay, thank you.